Most developers learn Python through the lens of traditional object-oriented programming. You define a class, instantiate an object, and assume the language is building rigid, self-contained structures under the hood, much like Java or C++. But mapping compiled language concepts onto Python creates a flawed mental model. When you assume objects are rigid, the dynamic behaviors of the language become technical anomalies, making advanced debugging nearly impossible. Python operates as a dynamic runtime type system, constructed entirely from discrete blocks of memory. The physical reality of the language is that everything, every integer, string, and function, is built on C-level structs, metadata descriptors, and function pointers. To see how this actually works, we have to track the exact path from the layout on the bare silicon of your RAM up through the CPython C structures, and finally to the high-level Python behavior you see in your editor. We are going to strip away the high-level syntax entirely. Looking directly at the raw memory addresses is the only way to accurately observe Python's execution model. Treating Python as a black box is a liability for systems engineers. Mastering the underlying memory model is a strict requirement for building high-level architecture. Whether you are working with a simple integer or a massive neural network tensor, every single Python object physically exists as an isolated block in your computer's RAM. This diagram shows the memory layout at runtime. Every object begins with the exact same memory header. This is a C struct called PyObject. A C struct is a custom data type in C programming that groups different variables together under one name in a continuous block of memory. The first component of this struct is the reference count, or OB_ref_count. This field is purely for memory management state, tracking exactly how many variables are currently pointing to this exact memory address. Below the header sits the object-specific data. If we create a simple string, the payload hello is stored right here. Notice what is missing from this memory block. The object contains state and data, but it contains zero execution logic. This means the hello string object does not know how to print itself, concatenate with another string, or format its text. To get those instructions, it relies on the second part of the header, the type pointer, or OB_type. A pointer is simply a variable that stores the specific memory address of another object. At the bedrock level, Python objects are strictly separated into dumb data containers that must blindly follow the directives of an external metadata pointer. To find those behavioral rules, we must follow that type pointer across RAM to its destination. This block is the destination, the PyTypeObject. This is a massive C struct responsible for storing all type information and behavior maps for a given class. The top section contains the identity field, TP name. This simply stores the string representation of the type, in this case str for string. Next is the basic size, or TP basic size. This exact metric dictates the precise number of bytes the Python interpreter must allocate in RAM whenever a new instance of this type is created. Below the identity and size data is the behavior partition. This area is populated with function pointers, variables that store the memory addresses of specific executable C-level instructions. We see this in action with a basic high-level operation. When typing 3 + 5 in your editor, you are writing standard Python syntax. The mechanical reality is that the interpreter intercepts that plus sign and executes a specific pointer call, int_type.tpadd, passing in the 3 and the 5. At the raw machine level, the CPU reads the address in the tpadd pointer and performs a direct jump to that block of execution logic. What developers perceive as intuitive, object-oriented operations are physically just mechanical pointer lookups and CPU jumps orchestrated by the type object. Built-in C functions operate this way, and Python uses the exact same mechanics to handle custom, user-defined class behaviors. This struct is a PyTypeObject for a custom class named dog. Inside this struct is a field called tpdict. This dictionary is the physical storage mechanism for every method defined inside the custom class. When you call the bark method on a dog instance, the system executes a dictionary lookup, mapping the string name bark to the corresponding function pointer. This same pointer logic applies to inheritance. In Python, inheritance is not a physical nesting of code blocks within each other. It is simply an array of pointers. This array is stored in the TP basis field. It points outward to the PyType objects of the parent classes, linking the dog class directly to its animal parent. The system traces this pointer chain all the way back to the ultimate base type, simply named object, which provides default implementations for operations like representation and hashing. This creates a strict recursive hierarchy. Types create classes, and classes create objects. But at the very top of the chain, the type of type is simply type. Because classes and inheritance are just dictionaries and arrays populated within a C-struct, what we call a class definition is actually just a highly structured state of memory. If classes are strictly defined C-structs in memory, we have to look at how Python allows developers to alter them while a program is actively running. This split view shows the execution of dynamically reassigning a class method, a practice often called monkey patching. Running the code dog.bark equals new bark instantly reassigns the pointer in the dictionary. Dynamic typing relies entirely on the physical overwriting of pointer addresses inside the tpdict struct. You can take this a step further and bypass standard class syntax entirely by invoking the type constructor directly in your code. Calling type with the class name, inheritance tuple, and method dictionary explicitly commands the system to allocate a new PyTypeObject in RAM. It populates the dictionary and registers the TP bases on the fly. This brings us to metaclasses. A metaclass is a control mechanism that intercepts this type allocation process before the struct is ever finalized in RAM. Major frameworks like Django and SQL Alchemy rely heavily on metaclasses to automatically generate and inject complex database behaviors into structs during initialization. Metaclasses act as preprocessors for generating PyTypeObject C-structs. Without mastering the struct layout, the underlying execution of these frameworks becomes impossible to trace. Zooming out, a running Python program is a massive network of structs, thousands of data containers constantly routing requests through type pointers. This network of memory blocks maps directly to the standard debugging tools senior developers use to navigate codebases: ID, type, and dir. This terminal execution reveals the architecture. The ID function outputs the physical RAM address. The type function exposes the ob_type pointer, bridging data to behavioral metadata. Finally, calling dir exposes the internal key-value pairs inside the tpdict structure. Python is a strictly structured environment comprised of three core elements. The first is state, the second is metadata, and lastly, transformation functions. This specific architecture, the partitioning of data into state, metadata, and transformation logic, is the common structural logic found in database storage engines and neural networks. All of these systems function by manipulating structured state transitions. Moving from an intermediate developer to a systems architect requires abandoning the illusion of self-contained objects. Achieving high-level mastery means embracing Python for what it actually is: a carefully engineered, highly dynamic memory manipulation system.